In chapter 6, we learned some applications of integration, and we now want to apply a couple of those to polar equations as well as rectangular equations. So the first one we're going to do is arc length. Now we learned the arc length formula back in chapter 6, and this is going to be the arc length for a polar curve. So the arc length is equal to the integral from a or alpha to beta of f of theta squared plus f prime of theta squared. Should look familiar, and it will come back a bit in Calc 3 as well if you're interested. All right, so it's not really a formula we generally have you memorize, but it's something you have to know how to apply. Now, when applying this, you want to make sure that you're applying it to only one period, not 2 or 3 or 4 or whatever, only once. So it's really important that you learn how to be able to find that period in Desmos so that you can kind of make sure that you're tracing it out only one time. I mean, you can kind of do it by trial and error as well, but it's easier if you do it in Desmos. Okay, so let's find the arc length of this cardioid, which is 2 minus 2 cosine theta. So I'm going to go to my computer, and I'm going to look for the period. Now, again, to do this, I have it graphing 2 minus 2 cosine theta, but I added in the little code that theta is less than or equal to d, and then I added a slider bar for d. This part is just getting me the point, right? R cosine theta, R sine theta, but for me, theta is d. If you don't want the point, you don't have to have it, but you do need the curve portion. So I'm going to go from 0 out to, there we go, it's 2 pi. All right, so 2 pi is my period for this graph. All right, so, and I want to know basically how much distance that was to get around the curve. That's what I'm finding. So the length of the arc for one circuit would be going around this thing once. Now we'll make a note. Found with Desmos. Okay, so we need to have that somewhere because we're going to need that in order to have our limits of integration. Okay, so let's find L. L is the integral from alpha to beta of the square root f of theta squared plus f prime of theta squared d theta. All right, well, let's see here. So f of theta is, of course, the problem that was given to us. So if I write it right here, this is f of theta, right? F prime of theta would be the derivative of that, right? So the derivative of that would be derivative of 2 is 0, the derivative of cosine is negative sine, so there would be positive 2 sine. I'm going to do that one right this time. All right, so this is equal to the integral. Now we just determined that that period was 0 to 2 pi. So the 0 and the 2 pi get us the limits of integration. That's where that comes from. All right, then a big square root. And then we're going to have 2 minus 2 cosine theta. And we're going to square it. And we'll add to that the derivative squared d theta. But the derivative, like I was saying earlier, is 2 cosine, 2 sine, my goodness, 2 sine of theta squared. All right, well, I can FOIL this out. So this is 0 to 2 pi square root. This is, let's see, 4 minus 8 cosine theta plus 4 cosine squared of theta plus another 4 cosine squared of theta, or excuse me, plus another 4, but this time sine squared of theta, d theta. That is 4, right? Because cosine squared plus sine squared is 1, and then there's a 4 times both of them. And 4 plus 4 is 8. So this is equal to 0 to 2 pi, the square root of 8 minus 8 cosine theta d theta, which is equal to, I could take this 8 out of there. So the square root of 8 times 0 to 2 pi, the square root of 1 minus cosine of theta. All right, now 1 minus cosine of theta is setting off a little bell in my head. So I'm going to go show you that from your trigonometry cheat sheet. So if you look at the half angle identity, let me zoom in real quick. So that half angle identity, sine squared of theta is equal to 1/2 1 minus cosine of 2 theta. Interesting. So I have 1 minus the cosine of theta in my problem. So if I took that and wrote it down, here, let me go write that. So note. So let's see, the sine squared half angle identity. Let me just kind of move this over so we can see what I'm writing. Oh, there's no good way to do this. Sorry, I'm gonna have to make it go away. So the half angle identity says that sine squared of some angle alpha is equal to 1 minus cosine of 2 alpha times half. Let me just do it that way. Okay, so that would mean that 2 sine squared of alpha is equal to 1 minus cosine of 2 alpha. So for me, 2 alpha is theta, right? So my 2 alpha here is theta, which means that this must be theta over 2, because that's half as big as that. So that means that 2 sine squared of theta over 2 is equal to 1 minus cosine of theta. Now all of this helps me make a change. So I can say that this is, well, 2 square root of 2, because the square root of 8 is 2 square root of 2. 0 to 2 pi square root, and instead of 1 minus cosine of theta, I can put in 2 sine squared of theta over 2 d theta. Well, how did that help? Well, I can take the square root of 2 out. Square root of 2 times square root of 2 is 4. So that would be 2 square root of 2 times another square root of 2. And then I'm taking the integral of 0 to 2 pi of sine, because the square root and the sine squared will undo each other. And it's the sine of theta over 2 d theta. All right, well, the integral of sine is negative cosine. This is theta over 2, though. So if I was going to say u is theta over 2, then du would be 1/2 d theta. So I would have to multiply everything by 2. So u equals theta over 2. So du is equal to 1/2 d theta. So I would put in 2 du is equal to d theta. So 2 du goes in there. So I have a 2, another 2 from these ones, and then another 2 from that 2 right there, which gets me 8. So that means that I have negative 8. Integral of sine is negative cosine. So negative 8 cosine of theta over 2 from 0 to 2 pi. And again, the 8 comes from, there's a 2 here, there's a 2 here, and there's a 2 right here. When I put in the 2 theta, right, if I was going to show all the substitution. I kind of skipped over the substitution part. It's there, but that's where the 8 comes from. All right, and the integral of, let's see, that would be negative 8 cosine of pi minus cosine of 0, which is negative 8 times negative 1 minus 1, which is 16. And since this was millimeters, it's millimeters. It's a length. It's literally the distance around. It's not an area. So it's going to have the same unit as what your function was measured in. Now, if you don't believe me, of course, we can double check it in Desmos. Okay, so I want to find the arc length. So I'm going to find the integral. And then I wanted from 0 to 2 pi. And then square root. And then it was 2 minus 2 cosine, I'm just going to use x squared plus 2 sine of x squared dx. And there we have it. It's 16. We were right.